Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Greetings and welcome to my channel, Preparing for Organic Chemistry. In this multi-part series, I will introduce and teach you 5 essential topics and skills that, in my experience, having taught the subject for many years and now tutoring students in undergraduate organic chemistry, are essential for success. But first, a little bit about me. My name is David Jeffrey, and I have a PhD in organic chemistry from UC Berkeley, with additional graduate coursework from Harvard and postdoctoral research experience from UCSF Medical Center in San Francisco, as well as from Stanford University. As I mentioned, I've been teaching organic chemistry for many years, although more recently I am retired from full-time teaching positions, and I devote my time to tutoring students in undergraduate organic chemistry. Although I have had a varied career, including working in the environmental industry, consulting, and most significantly academics, it is teaching and helping students that has always been my main passion. I'm a very effective teacher and apply conceptual methods in teaching complex content to my students with a de-emphasis on rote memorization. So again, welcome to the channel. I think you'll enjoy the video course that I have put together in teaching these 5 essential skills, and I'm confident that you will find the content useful and relevant in setting you up for success in your own organic chemistry class. So let's get started. On this slide, I list these 5 essential topics and skills that I have identified from thousands of hours, literally, of instruction and interaction with classes, small groups, and individual students that, in my experience, are essential to success in organic chemistry. And by this, I mean that these are 5 skills that you as a student poised to take your first course in undergraduate organic chemistry should have mastered before the first day of class. I want to be very clear about that. So what are these skills? Number 1, Lewis electron-dot representations. Number 2, isomers. Number 3, spatial aspects. Number 4, acids and bases. Number 5, reaction mechanism. So let's get started with these 5 topics. But before we do, we need to at least recognize the 2 main bonding theories in modern chemistry. And so let's spend a little time talking about that, and that will lead very naturally into the first of these skills, Lewis electron-dot representations. So here are the 2 main bonding theories in modern chemistry. The first being valence bond theory, the second molecular orbital theory. Let's now spend a little time and at least list and describe some of the key aspects, assumptions, and differences between the 2 theories. The valence bond theory is the first or original chronologically of the 2 main bonding models in modern chemistry. This slide lists some information and assumptions of valence bond theory, and I'm going to let you read this for yourself, but I will just point out a few critical features. The most important thing to appreciate about valence bond theory is that it's a localized bonding model. In other words, atom A in geometric proximity to atom B is assumed to form a covalent bond involving a pair of shared electrons using the valence electrons from each of the 2 atoms. And what we do is focus on that discrete bond between those 2 specific atoms, A and B. For more complex molecules that have more than 2 atoms, and of course many do, we look at the molecule via a bond-by-bond manner, where A bonds to B and B bonds to C, and so forth. This is the fundamental principle of valence bond theory, and out of this principle, an extremely useful device that we refer to as Lewis electron-dot structures comes, named after Gilbert Lewis, who taught at Berkeley around World War I. In contrast to valence bond theory, molecular orbital theory, which was developed after valence bond theory, especially with the advent of modern digital computers, molecular orbital theory looks at all of the atoms of a molecule and their contributions in forming what are called molecular orbitals. These molecular orbitals are mathematically formed by a process called LCAO, or linear combination of atomic orbitals. And as you can see in the slide, what this means is that atom 1, with its atomic orbitals, makes a certain contribution in forming a molecular orbital. And that contribution is contained in a weighting coefficient, denoted by C. Each atom makes its own contribution with its atomic orbitals and weighting coefficients. And in this manner, molecular orbitals are mathematically constructed from the atomic orbitals that are inherent to each of the atoms involved in the molecular structure. Once these molecular orbitals are formed, they are then populated with all of the electrons from all of the atoms, applying the same principles that you're familiar with when loading electrons into atomic orbitals. So conceptually, this is a very different approach than valence bond theory. You may be wondering which is better. They both have their strengths and weaknesses. Molecular orbital theory was embraced by the chemistry community in that it satisfactorily explained phenomena that valence bond theory could not or did not in a very credible or elegant manner. However, when you take your organic chemistry course at your college or university, you will learn organic chemistry almost strictly via the valence bond theory. You may wonder why the older model is still in use when the newer model explains more phenomena. And the reason for this is that valence bond theory, even with its deficiencies, satisfactorily explains thousands and thousands of phenomena in organic chemistry very nicely and in a manner that is easier to understand and apply than molecular orbital theory. To wrap up this brief discussion of bonding theories for our mini course, let's take a look at the valence bond and molecular orbital treatments of a simple molecule, ethylene. In this slide, you see the valence bond treatment of ethylene, which involves a double bond between the two carbon atoms. On the left-hand side of the slide, you see what we call Lewis electron-dot structures. This is basically an accounting of electrons to describe the bonding and connectivity of a covalently bonded molecule. And organic chemistry is almost exclusively covalent versus ionic bonding. You can see from the two pictures on the left that one can specify a pair of dots or one can specify a line between two atoms. They mean the same thing. What they mean is a pair of shared valence electrons that arise from the mutual contribution of one valence electron from each of the two proximate atoms. In the bonding between the carbon atoms, you see four dots or two lines, and that's because that's a double bond. On the right-hand side of the slide, you can see that valence bond theory can give us a more detailed view if we want to understand the orbitals that are involved. And you can see that the carbon-hydrogen bonds involve the overlap between a hybrid sp2 carbon orbital and a hydrogen 1s orbital. You can also see from this diagram that the double bond between the carbons is really comprised of two different covalent bonds. One is the sigma sp2 end-on overlap, and the other is the 2p pi side-on overlap, with each having different degrees of overlap. Compare the valence bond treatment that you just saw with the diagrams on this slide, which is the molecular orbital treatment of the same molecule, ethylene. You can easily see that the treatments are very, very different. And what you're seeing in the picture on the left of this slide is the formation of valence molecular orbitals coming from linear combination of valence atomic orbitals. And note that you see both sigma and pi type molecular orbitals, which has the same meaning as they do in valence bond theory, except now you see sigma and sigma star and pi star. The molecular orbitals denoted with a star are anti-bonding orbitals, which is a concept unique to molecular orbital theory, which have unfavorable energy that is equal to the favorable energy associated with a bonding orbital. This is because atomic orbitals are wave functions, and they can add either constructively or destructively in phase or out of phase. The diagram on the right depicts what these molecular orbitals look like in terms of electron probability density at the nuclei of the molecule, and the weighting coefficients that we mentioned before are embodied in these diagrams. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.